So welcome everyone to the ilifu online training workshop, and thank you very much for joining us today. And welcome back if you've attended previous sessions. So far, we've run an introductory session where we covered the basics of using ilifu services, and we presented an advanced session where we covered additional information on software environments and more advanced Slurm commands. Today, we're going to be presenting our third session, and then the final session will be presented next week, Tuesday, on the 23rd of September. I just want to start by introducing the ilifu support team. So Walter Salima is our astronomy support specialist, and Dane Kennedy is our bioinformatics support specialist, and Tinus Cloete is our systems administrator and also provides user support. And then myself, I'm Jeremy Smith, I'm the ilifu operations manager. And please note that these training sessions are being recorded. We make these recordings along with the presentation slides available from the ilifu website as a resource for everyone to use. We also go through a few demos during the presentations, which we've created a GitHub repo for so that everyone can access these as tutorials. And I'll share the GitHub repo in the Zoom chat during the presentations. We'll host a Q&A session at the end of the workshop where we can address any questions that you might have. You're welcome to post questions during the workshop in the Zoom chat if anything comes to mind, and the support team can address them at the time, but otherwise we can respond to any of your questions during the Q&A at the end. The topics for today include parallelism on the cluster. So that's using multiple CPU cores or multiple compute nodes to run jobs, which Dane will present on. And then Tinus will present on job resource allocation. So this is guidelines on how to determine what resources you should allocate to your jobs on the cluster, with the aim to reduce wasting resources for your jobs. But before I hand over to Dane, I just want to go through the support channels and where you can find information and help about ilifu services. You can email the support team at support@ilifu.ac.za. We have a ticketing system and a team of support personnel who will respond to any questions or issues that you might have. Our user documentation is available at docs.ilifu.ac.za. So I'm just going to flash it up. So it has a step-by-step guide on requesting an account, how to access ilifu, dealing with SSH keys, or how to change your password. So these are topics we've covered previously. And then some of this is expanded on further in the technical documentation. And there's domain-specific information here, astronomy and bioinformatics. And today's topics, Dane will be covering parallelism, which is under running jobs on the cluster, so parallel computing on the cluster. And Tinus is going to cover information that's under resource allocation guides. And then we have the ilifu status page. So this is provides status information about the ilifu cluster. You can see a general status at the top, and you can look at different components and drill down and check if components of the ilifu services are operational. And if we do have an outage, we'll post information about the outage and indicate that on the status page. So please do come and check the status page if you're experiencing any issues with any services, because we might have alerted users through this medium. And then, yeah, as I mentioned, the videos are recorded and you can find them on the ilifu website at this URL, and the GitHub tutorial material is available at this repo, and I'll post that in the Zoom chat as well. And I think that's everything from my side. So I'm going to hand over to Dane, who's going to take us through parallelism.
Good morning, everybody. Let me just get these things out the way. Here we go. Thanks very much for coming this morning, giving us your time. I hope this is useful information and that you'll be better at parallel computing by the end of my talk, or at least you'll know the right questions to ask. So yeah, my name is Dane Kennedy. I've been with ilifu for 7 years now as bioinformatics support. I'm also involved with maintaining Slurm a bit and various other little projects like our user website and things like that. So yeah, this presentation isn't, I've got some notes here from these ridiculous slides where it says Slurm basing and jab shielding, which is not what this slide is about, this presentation. Rather, I'm going to be talking about parallelism and how do we achieve that on the Slurm cluster. First, a quick review of ilifu's resources. So ilifu is a cloud computing facility, technically, but the bulk of our resources are sitting in our Slurm cluster. So what is our Slurm computing cluster? It's a collection of servers or nodes. Those terms are used pretty interchangeably, servers and nodes, that are combined to work together in a way that is more powerful than the sum of the individual parts. In this case, the individual parts consist of a login node, and this is the main interface you'll usually be using on the cluster, that or maybe Jupyter. And then we've got the compute nodes. The compute nodes are grouped together in what we call partitions. Today I'll be using the main partition, which is where most of our resources are. Most of these nodes have around 32 CPUs or cores and around 240 gigabytes of RAM available to use. Then we've also got other components of the cluster as some permanent storage. So we've got something like 8 petabytes of storage now, maybe creeping closer to 10 actually. And we've got several fast networks connecting the nodes together and the storage and granting everything access. Yeah. So modern data sets in both bioinformatics and astronomy have grown so large that it's becoming increasingly rare to be able to do meaningful research on our own PCs or laptops, or even large individual servers that we might find in our labs. We're usually limited by the amount of memory, CPU, or storage available on these devices. And that's when we need to look at large resources such as a computing cluster. And that's also where we take advantage of parallelism. So what is parallelism? The Oxford definition of parallel processing is a mode of operation in which a process is split into parts, which are executed simultaneously on different processes attached to the same computer or different computers attached to the same cluster. A cluster includes many connected nodes, each with its own RAM and CPUs. So yeah, a node is a single computer, server, virtual machine, or box. So work is partitioned into smaller jobs, sometimes with a partition of the data set. And I'll get into what that means a bit later. So we have several different kinds of parallelism, ranging from embarrassingly parallel problems. This is where individual parts of a computation are not dependent on other parts of the computation. I have an example from astronomy, which I think is vaguely correct. And that's if you imagine in radio astronomy, if one is doing signal processing in a volume to create a three-dimensional image of some region in space, individual pixels, at least computationally unrelated to one another. So if we're processing this data, all these pixels can be done independently of each other. A good example for parallelism in astronomy. Sorry, that's the same thing. Another class of parallelism is where individual components are highly dependent on each other. Here, an example from the bioinformatics world might be where we're doing a protein folding simulation, where we're modeling individual atoms and how they're interacting with each other and maybe the medium they're in. So in this simulation, we typically break up our larger volume of atoms into smaller volumes, but there is interaction between these smaller volumes. So let's talk a little bit about what a computer program is. This is a very simple serial program. It's just instructions that are run one after each other. So it's a set of discrete instructions. We can read them clearly one after another. They run one after another. And this example would print out the average grade of a class. So the simple algorithm would be, we initialize some value to 0, total value to 0. Then for each grade in the set of grades, we add the total, we add the value to the total. So the total is total plus grade. And we loop through each of those grades. And once we've done all the values in this set, we find the average by dividing the total sum by the number of grades, and then we print it out. So that's pretty trivial, and I'm sure you could have done that 15 years ago without much difficulty. But what if we wanted to do this in parallel? Again, reasonably trivial, but what we could do is partition the set of grades into n sets, and then do the following. So for each set of grades, we run through the same algorithm where we find the average of that subset. And then at the end, what we're going to do is combine those averages and then divide by the number of partitions or sets that we had. So if we had 20 numbers, we could divide the average of the first 10 and the second 10, and then add those together and divide it by 2, for example. So compared to the serial or sequential process, parallelism is more complicated. It requires multiple portions of a program to run simultaneously. This has several requirements. First, we need to have several resources available simultaneously. So this is where we may have several CPU cores. Obviously, if we're on a single core machine, we can only run one thing at a time. So there you have you can simulate parallelism by doing the separate parts, but you're not going to get any benefit from it. We also need the software to have been written in such a way that it can take advantage of these resources. In other words, we cannot simply take a piece of software and expect it to run better or faster simply by running it on a machine with more cores. The software has to be coded with parallelism in mind. And this involves some overall control or coordination. So these are ways for individual parts of the program to communicate with each other. Typically, this involves one part of the software being in charge of the overall plan. Excuse me. So this tells the other bits of software which data to analyze and combine the results at the end. This can be done in various ways, but is usually achieved with frameworks or libraries such as MPI, which is a message passing interface. There's traditional threading, and then there's OpenMP, which is open multiprocessing. And this is a framework for doing threading. So it kind of simplifies threading in a way. Excuse me. So parallelism on a computing cluster can look a bit different depending on the problem you're trying to solve. So as we said before, a cluster includes many connected nodes. Each node has its own RAM and multiple cores. Some of the nodes have GPUs, which is a whole extra class of parallelism. The work of a job is partitioned into smaller jobs, and sometimes with a partition of the data. So a small note on the way our physical hardware is set up. We do not have a low latency network like the CHPC. They've got an InfiniBand network. When we talk about latency, what we mean is the time it takes for even a small message to get from one node to another. The implication is that if you have the kind of problem where there is a lot of communication between nodes, like the protein folding example I mentioned earlier, then spreading the problem across multiple nodes can actually have a negative effect on your overall computation time, because you end up spending a lot of time waiting for communication between nodes rather than doing the computation itself. So if you have that kind of problem that requires that, you're better off using, say, the CHPC, which is an InfiniBand network. Our network is quite high bandwidth though, so while might be a relatively large delay in sending a message between nodes, you can send a lot of data. And that's one of the reasons ilifu was set up in the way it is that many of the classes of problems in both bioinformatics and astronomy fit well in this kind of setup where you don't need lots of inter-node communication, even if we are looking at large data. So with any luck, I haven't scared you off. So typically parallelism is implemented using one of three mechanisms. It can be on a single machine or node that has multiple cores. Most modem CPU have this. This would usually be done using threads or OpenMP. Multi-threaded code works well on multi-core machines where there is shared memory because different parts of the software running in threaded code, running in parallel can communicate directly with each other. There's no need to go over an external network. GPUs are usually used in scenarios where you can run exactly the same bit of code on different parts of data simultaneously. This is a bit different from threading, where the actual code running can be somewhat independent and doing slightly different things. And when moving over to multiple machines at the same time, we usually use the MPI library, which makes it easy to distribute work over many tasks. In our case, Slurm, which is our scheduler, will set up the environment. By this, it means it will allocate the machines for the job and tell the job how much memory and CPU is available. MPI can then use these resources to split out the parts of the job where they should run and combine the results together at the end. If you are using Singularity, remember that a container is kind of like a standalone machine with its own operating system and software, and you will need to ensure that you're using the same version of MPI inside and outside the container. And then we have something like hybrid parallelism, where we're combining multiple kinds of implementations. So you might use MPI together with OpenMP. These are fairly advanced scenarios, which we don't really need to worry about too much today. You can always contact us on the help desk if you want help. By default, a job in the cluster will only have a single CPU allocated to it. And this is what you'd use if you know your code has no parallelism. Perhaps it's kind of pre-processing work where everything needs to be done sequentially. The next level of complexity would be using threading or OpenMP. Here we will be requesting multiple cores, but only a single node. In the job script later, I'm going to do a little demo a bit later, but in the job script later, we will specify a single node, a single task, but multiple CPUs per task. Usually, you need to tell the software how many threads to use. In the case of OpenMP, this can be done by setting the OMP num threads environmental variable. Otherwise, it can usually be done by giving it a command line parameter. This is important as some software might mistakenly assume all the cores in the machine are available to use, but this might not be the case as your job will be restricted to what you've requested for it. And sometimes it's not explicitly clear that your software can use threading or OpenMP. For example, if you use NumPy in a lot of your calculations, there are quite a few operations in there that have been coded to use OpenMP and will take advantage of multiple cores if they're available. And finally, an MPI job requires one to use multiple tasks. And these could all be on a single machine or spread out across multiple machines. The number of tasks cannot exceed the number of CPUs on the machine. Most of our machines have 32 cores. But there's some with 48 and 96 even. Yeah, I think that's what I wanted to say about this. So the next thing I want to talk about is several scenarios for parallelism that you want to be considering for analysis. But here's a list of the parameters that you can set in Slurm that affect how the parallelism might work. So first we want to specify the number of nodes. That's the number of nodes allocated to the job. The number of tasks per node. So this can mean the number of CPUs you want to allocate to the job, but you could also have multiple CPUs per task. So if you have 16 tasks on a node, they might all need 2 CPUs. That could use all the CPUs on the node, but split up in various ways. We can specify memory in 2 different ways. We can say how much memory we need per node or per CPU. And you'll know what you need to use based on what your computation. Sometimes people need to scale by the number of memory by the number of cores they're using, but sometimes you'll scale, it's more fixed and you can just specify the memory. Then, sorry, I got tasks per node twice. I must fix this slide. So let me just go through the various scenarios that we're going to look at. First off, we're looking at serial and multi-CPU jobs. So if code is serial, it's not using OpenMP or MPI or threads. So increasing CPUs or nodes will not decrease execution time. You'll just have CPUs allocated to your job and they're idle and wasting resources, basically. So this is the most simple scenario and essentially what the default is, but you're specifying a single node, 1 task per node and 1 CPU per task. Then you would run your script. However, if we need to use multiple CPUs within a node with OpenMP, say, or threading, depends how clever what your Python script is doing. Here we're setting n as the number of CPUs. So here again, we're limiting ourselves to a single node and 1 task per node, but we are saying that we need n CPUs for the task, and we're setting some memory. We're behaving ourselves by exporting this OMP num threads variable so that we don't accidentally try and use more CPUs than we should in our job. You don't have to worry about breaking the rules because your job will never use more CPUs than are allocated to it, but it might actually decrease the performance of your job if it's trying to use more CPUs than are allocated to it. Yeah, and it's important to note that with parallelism, things don't always scale linearly. So there tends to be a point where increasing parallelism doesn't result in a speed up and can actually end up slowing things down. So it's very important to test your code and understand how it scales and performs. The next scenario where we've got multiple tasks. So in this is somewhat related to the previous one. In this case, we're using MPI. We specify multiple tasks, a single CPU per task. In this case, it's using MPI. So we're running a script, this Python script with using MPI. So there, essentially, the script gets run n times individually, and MPI is coordinating how they talk to each other, and can actually be spread across multiple nodes. And the second example, we're limiting it to a single node, but we would have to make sure that n is less than the number of cores on a node, whereas this could potentially scale much larger, this first example. And finally, we've got jobs spanning multiple nodes. So in this case, we've increased our nodes to some value n, and we've got multiple tasks per node. So in this case, we could have this Python process will end up running across multiple nodes and several times in each of those nodes, and then they'll all be talking to each other. Depending on how much they need to talk, it could be slow. I think that's pretty much all I need to talk about for this slide. Oh, this final little example here is maybe a script where we've got multiple CPUs per task. So it's a hybrid job with using MPI and OpenMP. So their OpenMPI, when it runs a task, it will know that it has multiple CPUs per process. But don't worry if that doesn't mean too much to you. Yeah, let me give you a quick little live demo which shows these scenarios. Hopefully you all remember how to connect to our Slurm cluster. In my case, I do that. I've set up a little, sorry, if you go to this GitHub repository, the tutorial information files can be found. I've already downloaded it and I've put it in my own directory here. Essentially, what it is I've got a number of Slurm batch files, which I'll show you in a moment. The main Python process is very simple. Essentially, it adds the numbers from 1 to 10,000, and I think it prints out the sum of them. But it's done in such a way that depending on how we've allocated the job, it'll be split up to multiple CPUs and nodes. As an example, we'll start with our single core, single node job. So let's look at the job script. As I always say, please remember to give your job scripts a good, sensible name. So when you're looking at your old jobs, you understand what they were. We've requested a single node. We said it has a single task, and each one of those tasks needs a single CPU. Been very generous for this by asking for a gigabyte of RAM. And we've said it shouldn't take longer than 1 minute to run. And we've set up some nice logging. So output files will be written to, I'll show you in a moment what the files look like. And what you won't normally have is this reservation line. I've just got it here so that my jobs can run even if the cluster is busy. We set aside a little reservation of nodes. But yeah, what the job is then doing is it uses this OpenMPI module. It activates a virtual environment that I set up, and then it runs our little Python script using MPI run. So if I submit this using sbatch, 1 CPU, 1 node, it's gone. We can see our job. It's already finished running, so the job state is running. It ran for 1 second, which isn't too bad. It ran on this compute node 206. So I'm just showing you these things so you can maybe have a sense of how to interpret the output of this at some stage if you're looking for yourselves. It says here it's created our standard error file and our standard out file. Yeah, so let's take a look at the logs. So if I look in my logs directory, we've now created 2 files. The error file is 0 size, so we know there wasn't any error output. And if we look at the standard output file, we see the output. So at the top of our Python script, it said, sorry, this is actually in the sbatch script, it outputs this line. So it says it's submitting the job. Then the Python script output this. So it says this process, rank 0, is running on computer 206. It added the numbers. Yeah, and it gave us. I think the important thing actually is to see the total time it took to run, which is 0.67 of a second. Looking at a slightly more complicated example, we're going to start expanding to multiple CPUs. So now we're going to look at our 4 CPU job, still single node. I imagine you can anticipate what it looks like. So the only thing that's changed now, apart from the name, is we're running 4 tasks on the node. Otherwise, everything else is the same. So again, we can submit this job. Check, can I type it faster? No, I can't. It's going to be completed already. Yeah, it's already finished. We can see that 4 CPUs were allocated to the job this time. That's the only thing that's changed. And this time, if we look at the logs, again, we've got nothing in our standard error, which is good. And if we look at the output file, we should see something slightly different. So now it started 4 processes, so it's running 4 individual times, but they're all running on the same compute. They've each got a much smaller subset of the data before, because there was a single process, it had all 10 million. This time it's only got 2.5 million. Each process has 1/4 of the share, of course. And our total time to run was reduced significantly from 0.67 to 0.22. So it ran faster as we might expect. And then we can look at the next level, which would be scaling up, doubling the number of cores once again. So this time we're going to have 8 cores on a single node. And it's going to be finished in no time. Completed as we expected. We had 8 cores allocated to the job again. Imagine you're anticipating what our output file is, how it's changed. So yes, now we've got 8 processes running instead of just 1 or 4. And we've got an 1/8 of the data per process, and our time decreased a little bit more. It didn't halve from 0.22 to 0.11, but it did get less. I think that might be expected. The interesting case is going to be now, where we now spread our work across 2 nodes. So if we look at this file, which is our 8 CPUs across 8 CPUs on 2 nodes. So now we've got 4 tasks per node, but we've got 2 nodes. So that's changed quite a bit, but it should, we would think it might have a similar computation time to the previous job, where it had also had 8 total processes running. But we'll check how it looks now. So let's submit it. 2 nodes. I'm not even going to bother doing that. Let's look at the logs. 8 CPUs, 2 nodes, standard output. So now we can see that we had processes running on 2 different sets of nodes, which is exactly what we wanted. The data sizes are the same because it was still just 8 total processes. And our computation, yes, was a little bit longer than the previous one. So even though we had the same number of cores allocated to the job, it took longer. And that's primarily because it takes time to communicate the results between nodes. So that slowed everything down a little bit. Yeah, I'm quite pleased that actually worked. If we looked at the total time, we should yeah, so we can see our total time came down, and went up as we expected. I think that's pretty much all. I think Quick reminder of the best practices. I think you get flashed this every time you sign onto our Slurm cluster, but remember not to run software on our login node. Before running large jobs, always make sure you've checked how your job scales. Tinus is going to hammer this into you next. And understand your jobs as well as possible before submitting and make sure they're working correctly. Rather don't do interactive jobs if you can help. Prefer to use SBatch. And remember to clean up your old files. So remember to keep your scratch storage as clean as possible. Delete stuff when you don't need it, please. And don't keep large files in your user directory. And ask us if you need software. You can use your own Singularity containers. We can help you build them. And that's about all I have to say for today. But please ask me questions at the end if you want to. Thank you.
Okay, thanks, Dane. Can everybody see my slides?
Yep.
Cool. Okay. So, hi everybody. For those that weren't at the last session, my name is Tinus Cloete, and I'll be talking to you guys about resource allocation today. Now, the ilifu cluster supports a lot of different projects. This includes astronomy projects and bioinformatic projects. But what they all have in common is that they all run in the shared resource environment. And each of these different projects have different resource requirements. So for example, some of the projects might require a lot of CPUs to run, some of them might require a lot of memory to run, some of them might require special resources like GPUs and so on. But the thing is that this is all there's also always a limited amount of resources, and it's important to use these resources wisely to give other people the ability to use them as well. So what I'm going to be talking about now is resource allocation, and basically trying to explain how you can do this. So how do you make your jobs that run on the cluster as efficiently as possible? How do you pick the right amount of resources? So for example, if you have a job that only uses 100 gigabytes of RAM, but requests 232 gigabytes, which is the maximum on most nodes, that means you're basically wasting that 132 gigabytes here. And obviously that's not ideal because somebody else on the cluster could have used that to run their jobs. So we've actually written up a resource allocation guide to take you through this. And most of this presentation is actually just going to be me breaking it down and trying to present it. But I would recommend actually going to the actual guide because it goes into quite a bit more detail. I'll give you an example of it. There's a link on the slide, but you can find it on our documentation, and it's just docs.ilifu, and it's resource allocation. So you can see this is the actual guide. Okay. Now, before going into detail, going into too much detail immediately, I just want to first talk a bit about the context of the cluster and all the different components of it. So you can just some of this might be a bit of a refresher, but I'm specifically going to focus on how these different components how the resources should be used on these different sections of the cluster. So first we have the login node, which you all should be familiar with by now. And then we have the main partition where most of the batch processing jobs are run. Then you have the Jupyter partition where you can log in via the web browser. I'm going to lump there's also a Jupyter development partition where you can test run Jupyter jobs, but without any dedicated memory. And then we also have the development partition there, which I showed in last time when I demoed interactive jobs. Then finally we have the high memory and the GPU partition. For these are more special resources partitions where you need a lot of memory or GPU resources. So now I'll be focusing more on the last three in this slide. So Jupyter, main partition, and high memory. Okay, now for Jupyter, what this is really a development space for writing and testing and debugging your workflows. You can use it to test new code. You can use it to develop your workflows and your routines. It's highly interactive, and you have tab completion. You can view doc strings. You can run subroutines in cells. You can even pull in images and have interactive widgets. It can even be a primary interface for stable workflows running on the cluster, specifically for cases where you need you might need some of the interactivity that Jupyter provides, or if you need to, for instance, preview images or of in between steps and so on. But in general, this is more focused on development. Then, well, this is mainly focused on development, as well as this for stable workflows that are harder to do directly as a batch job or just in Slurm, where you need more of a GUI interface, basically. Then for Jupyter, you've got different types of sessions, namely a shared. You have a shared resource session and a dedicated resource session. You will actually see this when you launch a new, when you try to launch a new Jupyter session, you will actually get this pop-up here on the right-hand side of the screen where you can pick development, pick a development session, or you can pick a dedicated resource session, which is the drop-downs at the bottom. And there you can actually pick the size of your specific Jupyter session. So in this case, you can pick 7 GB of RAM, 14 GB of RAM, all the way up to a full node of 232 GB. So the development session here is really only aimed at small development workflows that don't need to get dedicated resources. So if you're going to be running anything crucial, where you want to where you need to be sure that you have the right amount of resource, that you have dedicated RAM, then I would recommend using one of the larger sessions. But if you're just going to be testing things for lighter workflows, for smaller tasks, a development session in most cases should be fine. So with Jupyter, because it's an interactive environment, in most cases, the CPU is really going to be idle because it's basically going to be waiting for you to type in commands to run. So in general, memory is going to be your main bottleneck here. So what we've actually done is we've added a memory monitor here at the bottom of a Jupyter session. You can see it here. Let me see if I can highlight it here. So when you're actually running Jupyter, we actually show your maximum memory that has been used in a session. And this is the idea here is to give you information that will help you to try to pick the right size of session. So if you're going to be running a session that uses a lot of RAM, you can get a more accurate idea of how much actually was used. So you can pick the appropriate amount of resources for future sessions. Do note that we also do email people if they and notify them if the sessions Jupyter sessions that they created used a lot less resources than they requested. So for instance, if you requested a full node and you were only using say half of it or something like that, then we will generally alert users of this, and this is just because otherwise, again, because the resources are being used that could have been used by somebody else. Also, remember to try to shut down your sessions after you're done with them, because that frees the resources and makes them available to other people immediately. Otherwise, as you can see at the timeouts here, it might take a few days, well, in 18 hours of non-activity before the resources are freed again and made available on the cluster. You can do this by in the file menu, hub control, and then stop server. Unfortunately, I don't have a screenshot of it here, but we can go through it in the demo afterwards if you guys are not I haven't seen how to do that before. Next is the development partition. We covered this quite a lot in the last session, but this is basically just a single node that we have allocated, where people can run interactive, where people can run scripts, and specifically, it's especially useful to run interactive scripts and in general, it's used for testing workflows and pipelines. You can directly allocate a job on here by just running as interactive. And one of the big advantages here is that your jobs will be allocated here very quickly. Where if you were to try to get a bash job directly on the main cluster, you might wait a little bit longer because you're going to be getting dedicated resources. The development position is the resources here are shared. So it'll depend how busy that partition is. Okay, finally the main partition. This is the default Slurm partition. And in general, this is for stable, computationally heavy workflows and pipelines. You can use it to run many small jobs, or you can use it for very large jobs that require many resources. And we have seen both on the cluster. To some different projects might require different approaches of how the resources are being used. But in general, we do recommend that for really large workflows, it is better to first test on the development partition or the Jupyter partition by using subsets of the data or few iterations or something to make sure that it works. Because if you're running a huge workflow on the cluster directly without testing it properly, and then the job times out or fails or something else goes wrong, that could have been prevented easily. That does mean that during that whole period, the job was using the resources that time could have been used a lot better. So try to test your workflows first. Finally, we have the high memory and the GPU partitions. So the high memory partition is really for jobs that can't be split up easily into multiple jobs, then that make use of a lot of memory. So the largest job on the cluster is actually so it's the largest node on the cluster. I think has 1.5 terabytes of memory. But yeah, it is, and it can be. You can actually see it here. It's high memory 001. Oh, so high memory 003, I think actually. But it's but because there's only one of them, they could be quite a queue to get access to it. So it is good to make sure that your job actually does require that amount of resources and can't be split up. Then finally, there's the GPU partition. This is mainly for jobs that make use of GPUs. And ideally, jobs that only require CPUs should not be using this partition because you might be blocking those nodes for other people that do require GPUs. In that case, if you're only using CPUs, we'd rather it would be better if you just run your jobs directly on the main partition instead. Okay, so now we can finally get into the nitty-gritty of resource allocation. So with a job, there are three main types of resources that can actually be used. You have your CPU that can be requested. You've got memory, and you've got your wall time. The wall time is basically how long your job is going to be running on the cluster, specifically the maximum time. I do want to make a little bit of a technical note here, that CPUs, technically the computing nodes on ilifu has only 2 CPU sockets, and each of them has 16 cores, but so giving a total of 32 cores for a standard node. But in Slurm, these are referred to as CPUs as well. So I'll be in general. So basically, Slurm can see every node can be seen as having 32 CPUs. If I use the Slurm lingo, so I'll be using this terminology, but just a tiny technical note. Technically, it's actually cores, but I'll be referring to it as CPUs. Okay, so now how do you so what are the steps that you need to follow to allocate the right amount of resources to your jobs? It's actually quite the main thing is just to first find out how much resources your jobs need, and then only to request that amount. And it sounds really, really easy, but in practice, unfortunately, it can be quite difficult. The effect of doing this is that you'll avoid wasting resources, because you're not requesting more than you need. You'll increase resource availabilities for everybody else in the cluster. You'll basically allow other users to submit jobs and use those resources that are available. It'll also have benefits for your own jobs, because because Slurm uses a priority queue for job queuing. If you use less resources on the cluster, the effect will be that your fair share rating will not be decreasing as much. And this is the main factor that goes into determining your priority on the cluster. So you will actually be, in general, you'll have a lower waiting time for your own jobs as well. If you request less resources, or if you don't request more resources than you need. I've linked, I've added a link to our fair share documentation, so we can go more into detail there if anybody needs to, or you can just go read the link. But yeah, I'll leave that for questions afterwards. So okay, so now determining your resource requirements. I'm going to be breaking this up into 3 different topics, basically. So firstly, you can determine your parallelism of your software. This is really what Dane covered in the previous tutorial, or in the previous presentation. Then you can profile previous jobs to find out how much resources your previous submissions actually used, and then you can also scale up. You can test jobs and then scale up the resources required by those jobs to find out to determine the right amount to allocate for the larger jobs when you submit them. Now, when you're determining your parallelism of the software, most software packages actually only use doesn't have the ability to run to use parallelism, and it can only therefore use one CPU. So that's the first thing to have a look at. Some only support CPU level parallelism. That this means you can only run on one maximum of one node of CPUs, and then obviously you get task level parallelism, where you can have more than one node, and it can have a mix between CPU level and running across different nodes and across different CPUs on a node. In general, if you're using a package, I would recommend reading documentation on the package. So for instance, if you're using Casa, and see what the abilities of the software is. If your project is open source, there might be a GitHub page with more information as well. I think those are the first places to find more information about this. But in general, one thing to keep in mind with parallelism, even if your software does support parallelism, is that it doesn't scale linearly. So what I mean with this is that your maximum performance is often your least efficient way of running this. So, for instance, you can have your shortest running time or wall time, but you can be requesting a huge amount of resources that is completely unnecessary or inefficient. So for instance, you can kind of see this happening here on the chart here. So if you're requesting 30 CPUs or more, your wall time is really low in hours. You're only running for 5 hours, but you're using a really high amount of resources. Where in general, you kind of want to find a middle ground, because so you can basically you want to get the most bang for your buck. So what you want to do rather is maybe only use 5 or 10, because that gives you almost as good a wall time, but you're only using a fraction of the resources. So this is what I mean with the middle ground. Another thing to keep in mind here is if you're using MPI, by running something in a parallel way, you actually do induce an overhead. It's called a scatter gather overhead, because all of these different jobs need to be synchronized and basically managed, communicated with. So you can actually reduce your performance by making your job to parallel as well. But so you're in general the best approach to follow here is to try to break up your job into small independent pieces as much as possible. This is called the high throughput approach, and I'll be showing a simple example of this in the demo at the end. Now, in terms of finding your amount of resources that you require, you can now always look at the previous jobs to see how much resources you actually used. If you ran a very similar job in the past, and you want to find out what was the right amount of resources to request for future submissions, future similar submissions. To do this, what you can do is you can first find the job ID for that submitted job. So you can search for you search through the historical jobs by using the ACCT or ACE Accounting Slurm tool. And the useful parameter to know here is -- name. So you can use -- name equals and then the name of your actual job that was submitted to get to get a listing of all those previous jobs. You can also specify the start time and the end time if you know what the time frame was when you ran it. And then obviously you can use, well, not obviously, but as you can also use -x if you just want to see one line for each job instead of seeing multiple lines for each of the job steps. So this may just make it easier to look at the output. You can, if you can't remember the name of your job, you can obviously omit that and just look through your previous historic jobs between two dates or something like that. So once you have the idea of this job that you of a previous job that you ran, you can now look at the resources that were used. So the main thing here in terms of memory is to look at the max RSS statistic. So this is the max resident set size, and it's basically the maximum memory that your jobs used based on a sampling that was done every 20 seconds. So for instance, if you want to know what the max RSS is for job ID 1, 2, 3, 4, 5, 6, you can use saccount and then -j because that'll give you a job ID. And then you can use -o to specify specific columns that you want to display. So in this case, I just want to display the job ID, the job name, and specifically the max RSS for the maximum memory, and then also the requested memory for the actual to show what was the amount of memory that I requested for this job. One thing that might simplify the conversions is to use -- unit equals g just to convert units to something more sensible. Here I show an example of this. So you can see this job had a max RSS of 213 gigabytes, while it requested 232. So that seems quite decent. In general, what you want to do here is you don't want to use exactly the same amount of memory that you see in the max RSS for a few reasons. One of them is it's only sampled every 20 seconds, and there's also some random variation, but just based on your program running as well. So you really do want to avoid an out of memory error here, because if you're using more memory than you requested, obviously your program will probably crash. So in general, we recommend using 10 or 20% higher than what you see. And in this case, looking at 213, extra 10% there is about 20. So that kind of makes sense. But you also want to, on the other side, avoid excessive usage. So for instance, if it was 113 gigabytes, then requesting 232 would be excessive. Now, in terms of CPUs, here you can you can do something similar. But a really useful tool to know here is the SEFF tool, or short for Slurm efficiency. What this will do is it'll compare your allocated CPUs, how much CPUs how much of the CPUs the requested were used basically. And it actually shows this as a percentage. So for instance, if I wanted to monitor this job 1, 2, 3, 4, 5, 6, I could just run SEFF 1, 2, 3, 4, 5, 6 on the cluster. Note though that this does require the job to have been completed. So this is not for a live job. So you can use SEFF and it'll give you the statistics, and it'll show you in this case that the CPU efficiency of the job was 71%, 71.9%. I also give an example of a job that was not being resource efficient and only using a small portion of the CPUs requested. Here so SEF 2012880 only had a CPU efficiency of 1.17%. So it was only using 1% of the CPUs requested. This also does give you the same, give you the memory information as well. So so this is also useful, but note that this memory information is also based on the max RSS. So in general, SEFF is a very useful tool to get an idea for one specific job, just to see how efficient it ran. Note that you can also do this for Jupyter by just opening a terminal and then running SEFF and then your job ID. So in Jupyter, there's a file new terminal, and then you can just do it directly in Jupyter. Now, the other resource class is obviously your wall time. So this is the maximum amount of time that your job is allowed to run. So what you can do here is you can monitor the elapsed field or column in Slurm, which tells you how long a job ran, and then the time limit is the wall time or the maximum time that you specified that the job is allowed to run. So as an example here, you can I just used Ace account for this job, and I looked at the elapsed and the time limit fields. So you can see this job took 21 minutes to run, but 1 hour was specified as the time limit. So in general, what we recommend here is to use a bit of a higher buffer than for the memory. So example 20 to 30%. This will just avoid the job timing out, because if the job runs longer than the time limit, then Slurm will terminate the job. So you obviously don't want that, but you also don't want to allocate an excessive time limit for a job, because this will have this will make it slow for you to get allocated the resources for your job, because Slurm has to find a time slot of that length in and block out the resources for that for to be able to run your job. So in general, try to only use a 20 to 30% buffer. In this case, it was obviously quite a bit more. This, I think, was like a 200% buffer, which is quite a bit too much. What I should maybe note here as well, though, if your job actually completes, the job will obviously the resources Slurm will then recalculate and find and use free the resources and deallocate it and make it available for other jobs. So it's not as bad as the RAM and CPU where the resources are completely going to waste, but still it's good to not over allocate too much. Now, the other strategy that I want to speak about is scaling tests. So with scaling tests, what you're really trying to achieve here is trying to get a better estimate for the resources that your jobs are actually using. Specifically, your wall time might be quite difficult to estimate accurately, especially for long jobs. Because there might be other things that affect this as well. So, for instance, if you're running on a node where that's very busy, or if there are very high demands on the storage system, there might be or network or the network system, there might be some delays that make your job run longer, or it just might be more variable in general because of the type of computation that you're doing. So what you can do to get a better estimate for the amount for your jobs is to take a small subset of your jobs, to take your job and take a small subset of your data, for instance, and then test the wall time for that smaller version. In this case, it would be reasonable to over allocate because you're only running a scaling test, and you're trying to get information, and it's a lot lower resources. And in this case, because you're only testing, it's if you underestimate, you'll get feedback a lot faster. So this is really just the testing phase of trying to see how much resources are actually your job actually needs. What you can then do is you can repeat this experiment at a few sample points to see how much resources were used, and then kind of plot your resource usage as a function of say input or CPU, and just get and extrapolate to see how much resources your full job actually would require. So this kind of just gives you a better estimate based on empiric data, instead of just starting very high and then slowly decreasing based on how much resources we use for your full run. So this is just a more scientific approach to try to determine how much resources your jobs needs. Obviously, remember to add the buffer that I mentioned in the previous slides. So what you can also do to get information about actual jobs that are currently running is to use the stat command to get the max RSS statistic. But just note that in this case the units are in kilobytes, so you will have to convert this to gigabytes. And the other thing you can do is to get more information about actually jobs that are actually running is to SSH into a computing node. So if you have a job that's running on a specific node, we actually give you SSH access to that node to be able to SSH into it. So what you can do is for SBatch, you can, when you SSH into the cluster, just remember to use -a, because this makes it possible to forward your authentication. And then you can look at your SSH into the computing node where one of your jobs are running directly. They're just using SSH and then the computing node. With Jupyter, you can do something similar. Now, by just opening a new terminal. Now, once you're on that node where your job is running, you can now use a utility like htop to get more information about the resources that are being used by your job. So htop-u and user can be used to filter all of the processes running on that node to only your processes. And then you can actually monitor the resources usage in real time. This can be quite this can be a very good way of getting more information than and more basically to get real time information about the job and how much what is happening. So one thing that I think a lot of users aren't aware of with ilifu is that you have multiple Slurm. You can have multiple Slurm accounts. What I mean with this is, if you are part of different projects, you'll have a account for each of those projects where resources where jobs can be run, and also giving you access to the data of those accounts. With Slurm, you can when you submit a job, your specific account, the job will be running under the specific account that is under your default account, but there could be multiple ones. So, for instance, if you log into Slurm, if you log into Slurm login node, you'll actually see a list of all the Slurm accounts that you actually have, that you are a part of, and it'll also tell you which one is the default one. And when you're submitting jobs, you can change that account. So, for instance, if you're part of two big projects, I think a lot of users always use a splash and they submits their jobs, but that will only go to in that case the job will be running under the default account, where ideally it's better to specify the correct account for jobs that are being submitted, because you will have different priority ratings and so on for each of these accounts, and this just makes it possible for us to give you to basically determine how much resources you actually are allowed on the cluster. So you actually by actually submitting jobs to the correct account, this actually helps your own job times be lower, and helps us to monitor the resources of different accounts more accurately. You can do this by just -- account and then your name, and you can specify also change your default account by the command you actually see when logging into Slurm, or by running as help. This is a bit confusing. We can go through this in the demo. I'll quickly show you where this is. Okay, so this covers everything from my side. I'll just quickly be doing a short demo next. Okay, so let me first log into the cluster. So in this case, I am actually going to be logging into Node, so I'm going to be using SSH-A to forward to do authentication forwarding. Is my terminal large enough? Is there anybody?
Yeah, it's good.
Okay, cool. See if I can still remember how to log in. Okay, so this is what I was speaking about. So when you're logging in, you can see you have valid Slurm accounts. I'm part of the ID account, I'm part of the pipeline account, and I'm part of the admins account. And in this case, the admins is the default one. And then the command to change your default is actually shown here as well. When you're submitting a job to Slurm, you can use -- account equals, and then whatever the appropriate project is that you want to run the job under. Okay, let me quickly change to the correct folder. I'm just going to quickly clean up these. I want to clean the logs as well. Okay. Okay, so this is similar to my previous demo in terms of I've built a dummy workflow where you have a few scripts. First, I have a setup script that just does some initial setup of all the files and so on for your computation. Then you've got the calculation, which is script 2 calculate. This will be a memory intensive calculation that uses about 80 gigabytes of memory. And in this case, I'm going to be assuming you're not starting off with these two separate components. You're just starting off with a combined script. In this case, it's called script combined. And I'm just going to be, just for this demo, just to simplify things, I'm just going to be calling script 1 first and then script 2 calculation step. But in practice, what I'm trying to show here is most people start off writing their scripts. So I can maybe just show you what I mean. Yeah. So in this case, no, sorry, that's script 1. So that's a dummy version of the setup script. And this is the memory intensive portion. You don't have to worry about these details. This is just a dummy workflow to simulate some resource usage. And then this combined script is just going to be calling the one script after the other one. But in practice, what I want to illustrate here is most people would actually write an initial script, and that script would contain portions of setup code that might run a while, that just does a lot of setup, and mainly uses the CPU. Then you have a second portion, which does the actual calculation and uses a lot of memory and so on, which is what script 2 here is meant to illustrate. And that only starts running quite a bit later, and then that actually starts using the actual resources. But what you actually want to ideally do is you would rather want smaller independent scripts that you can submit and request the right amount of resources for. Because if you request for this little script, if you would request a lot of resources throughout that whole period, all throughout this initial script 1 run, you will have all of that resources allocated and not being used. So yeah, let's just show an example of this. So I've got a Slurm batch script for this. So in this case, you can see I'm just naming it combined script, and I'm requesting 80 gigabytes of resources, which is fine. And in this case, we don't know it yet. We'll test it now, but and I'm requesting it for 5 minutes, which is a quite short period of time. You don't have to wait for these last. You don't have to worry about these last 2 lines. This is just for this specific demo. And you can see here, all I'm doing is I'm running a Python command in a virtual environment, in a container, and I'm just running this combined script. So let's just let's submit that script now. Actually, I think, okay, so the script is being submitted. And we can actually see if it's running. Now you can see it's running here. We can watch it live. I think it takes about a minute. But yeah, so then the main thing is normally what you would have to do is you would be running this first the script, and then afterwards you'd be able to should be able to profile and see how much resources were used. Unfortunately, in this demo, the profiling is going to be a bit difficult because of the short time frames involved, and because we're only sampling the memory usage and so on every 20 seconds. So instead of using the efficiency command SEFF, I'm rather going to be logging into the node directly to show you the actual resource usage. But in general, the first thing to normally do would be to use the SEFF efficiency command. I'll show you what the output is here. So in this case, I'm running SEFF efficiency on the specific job ID. So you can see here that it is using 96% of the CPU. So it's very efficient in terms of CPU. And then it was only running for a minute, and I know I requested 5 minutes, so that's also quite good. The memory efficiency isn't great though. It's only showing 23%. But as I said, this is not that reliable for this demo. But in general, this would be very reliable. So if you're seeing very low efficiency here for one of your jobs, this probably does mean that you're allocating way too little resources, way too much resources. In this case, because it's only a very short period, it's not that reliable because it's only sampled once. So that sample point obviously was quite low. But what I would like to do now is to SSH into the node while the script is running. So let me just quickly open up Tmux so I can split the screen and just see what's. Let's rather do this way, I think. Okay. So let's. Since it's only a minute, I'm going to have to be quite fast here. But let's see. So normally what would happen is you would do a spat submission. You would then be able to go use SQ to look on which node the job is actually running, and then you would be able to SSH into that computing node. I've set it now to always run on one specific computing node because I only have a few seconds to SSH into the node. So I know it's going to be running on compute 206. So let's just do it like this. Okay. And then I'm going to run htop. I'm going to zoom into this terminal, and you should be seeing. I hope I got the node right. Let me just see which node this job was submitted to. Oh, okay, sorry. This was I think I submitted the wrong script there. I submitted the script directly instead of the SPatch one that specifies the node. So let's just try that again. So Slurm script. So combined. Okay, let's try again. Okay, so now there we go. So your script is running. So we can see it's running the first script in this case, and it's using 100% of CPUs and only 3% of memory. Yeah, at the top you can see, because I'm the only job running on the node, you can actually just use this directly. It's using about 9.7 gigabytes. Okay, so now as the script keeps running, we can keep monitoring it. It's still using. Okay, now the CPU usage dropped a bit, and I see the script 2 actually started running. And now we can see the memory usage actually climbing. 26, 30, 35, 40, 45, and we can actually see it's running all the way up to what's about 66, and I think the maximum here should be about 80. So you can see the connection now closed because we don't have a job running the job completed. So the max we saw here was 675. Okay, so you can see the job is not actually it's not using resources that efficiently, because for the first half of the job it's only using almost no CPUs, no memory, and then in the last bit it's actually using memory for the computation. So what you would rather do in this case is split up that job into two separate scripts. A setup script that does all the setup, and then a calculation script. I've already obviously done this now because this was the idea of the demo, but this is just to illustrate this. And then you could just submit those separately. So if I look at script 1 here, let me just zoom into it. So now I'm only requesting 10 gigabytes of memory, and for script 2, I'm going to be requesting 80 gigabytes as well, and then only for 2 minutes. And then you can submit both of those. You can obviously, if you wanted to profile the historic usage of it, you could also use the ACE accounting way to see how long the jobs actually ran. We obviously did all of this live now, but in this case, you could also use ACE account and -- name to get information about for the wall times to specify in that script. For instance, you could use ACE account and then name, and now I could if I wanted to know the wall times to specify, you could just use elapsed here, for instance. You could see, okay, in most of those cases it only ran for a minute, so it's probably fine to allocate 2 minutes to the job. So now I can actually submit. Let me just see the names of the scripts again. So now I can actually submit the separate portions, and we can look at the efficiency of those.
Tinus, we're getting close to 11:30,
Okay.
so we wrap it up, unfortunately.
Okay, no problem. So okay, but in any case, you would be able to since it's independent in this case, I can just submit both of them at the same time. But in general, you would actually have to wait for those for the one complete, since the second one to be submitted. Okay, so once we can, so how much time do I still have left? Just 2 minutes. Okay. Okay.
Is there any
Let's just check.
key points you want to raise?
Well, okay, so both of those are done. Let's just let me just finish the demo very quickly here. So in this case, I can look at the first job, and I can see in this case it's only using 7 gigabytes for the first bit, and it can use it's using well, in this case the sampling is not it only sampled 56 gigabytes. But so basically the memory usage is a lot better in this case. The resource usage in general for the script will be better if we split it up into separate components with the correct resource amounts for each of those. Okay, so yeah, I think that summarizes that completes the demo. Let me see any I can maybe just iterate some best practices. I think Dane already mentioned most of those. But yeah, so the main thing is just try to not run software on the Slurm logging node, and try to use the transfer node for transferring jobs. When you're running a large job, try to identify the available resources. Try to do these different tests that I specified to try to figure out what the right resources are, and don't request too much. And try to split up the jobs into separate portions that where possible. I didn't get time to show you how you would actually schedule those jobs to run after each other, but we did cover this in the previous presentation where we covered dependent jobs. So it is very possible to just do that. And then lastly, try to, if you're making use of Scratch, please try to clean up your files that do not that aren't being used, or clear out old raw data. Thanks.
Cool. Thanks, Tinus. It is quite late, but I'll open the floor to any questions. So if you have questions, you're welcome to raise your hand and unmute yourself and ask questions, or you can post questions in the chat. I see we haven't had any questions raised today, so hopefully Dane and Tinus's presentations were very clear. But yeah, we'll stick around for some time to answer any questions. Just as a summary, Dane's covered parallelism, so that's using threading or threading which uses multiple cores or CPUs, or MPI, which makes use of multiple nodes, and these can be combined. And what's kind of the key information or thing to take away from that is that it's very dependent on the software that you're using. Not every software has been coded for threading or for MPI, and so assigning additional CPUs or assigning additional nodes can be very wasteful. You have to research your software, make sure that it can be parallelized. But those are good. I mean, if you're writing your own code and you want to make use of parallelism, have a look at MPI and multi-threading. Python, for example, has packages for both of these. And yeah, Tinus has gone through resource allocation guides, so it's super important to understand the resources that your job needs on the cluster. Like Tinus mentioned, it's a shared resource space, and over allocating resources can be really detrimental because it wastes resources. So the resources that aren't being used or can't be used by other users. And really what this means is that there's if a lot of people are wasting resources or over allocating, means that there's reduced availability and ends up increasing the wait time for jobs for a lot of users. So kind of a regular thing that we get complaints about is long queuing time, a long wait time. And an aspect of this, there's limited resources, but the one aspect is that people do tend to over allocate resources and make use of more than they need. So please do consider the resource allocation guidelines that Tinus has presented on. Yeah, and Tinus's kind of key takeaway from his demo is really about if you have a job or a pipeline, different components of that pipeline are going to use or may use different number of resources. Some portions of a pipeline, like for example with Casa, the radio astronomy pipeline, some of those pipeline components are serialized and some can be parallelized. So you can use MPI for some portions of the code and use single cores for other portions of the code. So understand your pipeline and assign resources for the smaller components, break it down as much as possible, and submit individual parts as individual jobs. So we're going to have one more session, which Walter is going to be presenting next week, and that's going to cover data transfers and all the data transfers kind of software that we have available, and also on data management. So kind of similar to the resource allocation, but looking at the kind of the storage component, like how to structure a workflow to make the most of the storage amounts that are available. And Walter will also touch on Carter and the Soreo archive, using the Soreo archive next week. So I hope everyone joins us next week. We haven't had any questions, so I think we can end there. And I just want to say thank you again to Dane and Tinus for presenting. And thanks everyone for attending the training. Appreciate taking the time to join us.